We'll now discuss the list abstract data type. Our list abstract data type is just a general list of the form A0, A1, A2, all the way to AN-1. So we're going to say that the size of this list is n. There are n items in the list. And if the list is of size 0, so if there's nothing in the list, we will call it an empty list. Now for any non-empty list, we're going to say that AI follows AI-1. Sometimes we also say that AI succeeds AI-1, and here we're assuming that I is strictly less than n. And we'll also say that AI-1 precedes AI, where I is strictly greater than 0. We'll say that the first element of the list is A0, and the last element of the list is AN-1. This is just like how we handle the index for arrays. So here there are a lot of similarities between lists and arrays. It's just a list is kind of the general abstract data type. An array is one way to implement it, and we'll see how we can do that a little bit later on. Now we say that the position of element AI in this list is I. So think of I as like our index in this case. Now for all the examples that we're going to be doing here, we're going to assume that the elements in the list are integers. But that doesn't mean that that's the only thing we can store in lists. We could do characters, strings, doubles. I mean, we can have these arbitrarily complex elements in lists. And if we had to implement it, we can easily do that in Java or even C++ by using what are called generics. Now we'll talk more about generics in other classes such as our data structures course. We also need a set of operations we can perform on the list abstract data type. So we're going to take a look at least some of the common operations. We have things like print list, which just prints the contents of the entire list. We have make empty, which would clear the list. We have find, which would return the position of the first occurrence of a particular item. We have the insert operation, which would add an element at some position in our list. So we could have multiple versions of the insert operation depending on where we're inserting. We have the remove operation. So this would delete an element at some position. And then finally, we would have the find kth operation, and this would return the element in some position. I want to reiterate here with abstract data types, we're only listing the operations and what they are supposed to do. We don't mention here how they're being implemented. That would be done elsewhere. We're just mentioning some of the operations that would be included in a list abstract data type. Let's take a look at an example. Let's say our list is 34, 12, 52, 16, and 12. If we were to do find 52, then this may return 2, because it may return the index or the position of where 52 is located. If we did something like insert x2, so here we're trying to insert x at position 2, well, this list may become 34, 12, x, 52, 16, 12. And here we're saying it doesn't matter what the data type is, we can have numbers or letters or characters and so forth. If we were then to call remove 52, maybe this would turn the list into 34, 12, x, 16, and then 12. So the interpretation of what would be appropriate for a method is completely up to the programmer. And that's why we mentioned that these methods might return something. It just depends on what the programmer feels is appropriate for the definition of a method. This even is true for special cases. For example, let's say we were to call find1 in this list. Well, what would that return? Would that return like a -1 like we've done with our sequential search and binary search from before? Or do we have it return an error? I mean, it just depends on how the programmer wants to interpret and define that particular method. We can even include additional methods if we want to. We can include a next and previous methods, and that would take a position as an argument, and then it would return the position of the successor or the predecessor, depending on whether we're talking about next or previous. Clearly, we can use an array to implement a list. We've already mentioned that before, but we need to address one of the biggest problems with using an array. What if we need more elements than the size of the array? So what we can do in this case, if we find that the array is full and we need to add more stuff, we can create a new array and we can double the capacity whenever this is needed. Now, why are we doubling it? Because we really don't want to have to create a new array every single time we want to add a new element to our list. So doubling seems to be a good way to do it, because that way we can kind of cut down the number of times we need to actually increase the capacity of the array. So let me give you an example of some code that does this. So here in our example, we're saying we create an array. Initially it has 10 integers, or it can store 10 integers. And maybe we just do some stuff with it, and we find that we need a larger array. So we'll create a new array. So I'm going to call this new R, and we'll create a new integer. And the way we do this is we take the length of the original array, or the size of it, and you multiply it by 2. So in this case, new R should have 20 integer elements in it. And then what we can do is just we can go through all the elements of the original array and copy them into the respective positions in the new array. If we were to use the print list method, this can be done in linear time because we just print the contents of each element in the array. If we want to do the find kth operation, that can be done in constant time because we can pass this value of k, which would be the kth item in the list, and we can just directly access that element. That's one of the benefits with arrays, is we can directly access any element that we want. Now, if we have to do any inserting or deleting, that could be expensive depending on where we would do the insertion or the deletion. We've already mentioned this a little before when we talked about the common operations done with arrays, but just as a review, if we look at the worst case scenario, if we were to insert or delete at position 0, then that means we would have to push all of the array contents. So if we're inserting, we have to push everything over one direction. If we're deleting the first element, we have to push everything over in the other direction. So that means that these would take O of n time for both of these. The best case scenario would be if we had to do inserting or deleting at the end of the array, and that would mean that they should take constant time because we're just either tacking on an element at the end of the array or we're just deleting something at the end of the array. So what's our final verdict on using arrays for lists? Well, it kind of depends. So if inserting and deleting are done at the end of the array, and we're only using array accesses where we're directly accessing elements of an array, then the array is a pretty good option. It's a good implementation for our list abstract data type. Now, if we're doing inserting and deleting at other places in the list and not just at the end, then the array is not a great option just because of the extra time it's going to need to move all the elements around.